Okay, I'm going to go through the forces tutorial, and you might want to open up the tutorial so you can follow along with me as I go through the explanations. All right, two people are attempting to move a large block. The block does not move. That's an important statement right there. Chris pushes on the block, Pam pulls on a rope attached to the block. So let's draw a free body diagram. That's question 1A. They're essentially asking us to draw a free body diagram. Here's the block. Now Chris is pushing to the right. So there's the force of Chris on the block. Pam is pulling to the right, but she's pulling on a rope. So as far as the block is concerned, there is a tension force from the rope. So you don't directly include Pam's force. It's the tension force from the rope. Now, of course, there's gravity. And there's a normal force. The block doesn't move, so if there's two forces going to the right, then there must be a force pointing to the left to keep it from moving. So that's probably going to be a friction force. Or maybe the block is just glued to the floor, or nailed to the floor or something. But let's assume that that is friction. Friction force, the ground on the block. That would of course be static friction because it's not moving. Okay, label each force vector. All right. So I've kind of done part B here with my labels. Describe which object is acting on, which object is providing the force and which object is being acted on by the force. So there's the normal force, the ground on the block, the push of Chris on the block, the tension force, the rope on the block, the gravity force, the earth on the block, the friction force, the ground on the block. Okay, so we did part B. All right, part C. Which of these are contact forces and which are non-contact forces? So contact, that would be the normal force, friction, the push from Chris, and the tension. And non-contact, or field forces, gravity force is a field force, or non-contact. There are many different types of forces, including friction, tension, magnetic, normal, gravitational force. Categorize these forces. Okay, we kind of did that already, but we'll do it again. So contact forces out of this list would include friction, tension, normal, and non-contact forces from that list would be magnetic and gravitational. Part E, consider the following discussion between two students. Student 1, I think the free body diagram should have a force by Chris, a force by the rope, and a force by Pam. Student 2, I don't think the diagram should show a force by Pam. People can't exert forces on blocks without touching them. I agree with student 2 in this case. Pam is not in direct contact with that block, Pam probably can't apply a field force or a non-contact force to that block. So as far as the block is concerned, it just feels the tension force with the rope. So we only include the tension force and not an additional force from Pam. All right, part 2, drawing free body diagrams. Let's draw a free body diagram for this book that's at rest on a table. Here's the book. There's a coordinate system. There are 2 forces involved. There's the gravity force of the earth pulling on the book, and there's the normal force of the table pushing up on the book. The normal force keeps the book from falling. So what evidence do we have for the existence of each of these forces? Well, the evidence for gravity force is that in our everyday experience, there's always a gravity force pulling objects down toward the earth. And the evidence for the normal force is that this book is stationary, it's not falling. So there must be a second force to counteract that gravity force. So as I go through this video, I'm not gonna write down all of my explanations in words because that'll just take too long. So you can feel free to rewind and watch that explanation again. Also, there's subtitles on YouTube videos if you want to read what I'm saying too. What observation can you make that allows you to determine the relative magnitudes of those forces? I observe that this book is stationary. Its acceleration is 0, and by Newton's second law, that must mean that this gravity force exactly cancels out that normal force. They must add together to give you 0. So their magnitudes must be equal. And we can show that on the diagram by drawing these 2 arrows with the same length. Okay, now things are getting interesting. Let's put a second book on top of that first book. And we'll draw a separate free body diagram for each of those 2 books. I'll start with the upper book. The upper book, of course, experiences gravity. So I'll label that as the gravity force of the earth on the upper book, U for upper. Now the upper book is stationary, so there must be a normal force counteracting gravity. Normal force is always between 2 objects that are in direct contact. The upper book is sitting on the lower book. So the normal force comes from the lower book. So I'll write normal force of the lower book pushing on the upper book. Now, let's draw our free body diagram. For the lower book, the one that's underneath. That lower book is, of course, experiencing gravity. There's the gravity force of the earth pulling on the lower book. That lower book is getting squished by the upper book. That squish is the Newton's third law pair of this normal force. It's the normal force of the upper book pushing on the lower book. And that lower book is stationary. It is not accelerating, it's not falling. So there must be an upward force holding it in place. So there is the normal force of the table on the lower book, holding it in place. Now I do want to be careful with how I draw these arrows. I want to make sure that this normal force from the upper book is bigger than the gravity force on the lower book, because that upper book has that's got more normal force. It's got more weight. Okay, we had some more questions. Question 2. Explain why a force that appears on one diagram should not appear on the other diagram. In a free body diagram, you only draw forces that are acting on the object of interest. So within one particular free body diagram, there's only one object of interest. For instance, here's the upper book, and you can see that each of the forces have U as that second subscript. In this other free body diagram, the object of interest is the lower book. All the forces have L as the second subscript. So there can never be the same force in two different free body diagrams. What type of force does the upper book exert on the lower book? Well, we discussed that. It is a normal force. And it would be incorrect to say that the weight of the upper book acts on the lower book, because that would mean that we're considering the gravity force between the upper book and the lower book. And we're not concerned with that in this problem. In fact, the gravity force between two books, if we really wanted to be super accurate, we could draw that in this free body diagram, but the gravity force between two books is so tiny that it wouldn't matter at all. What observation can you make that allows you to determine the relative magnitudes of the forces on the upper book? Once again, this book is not accelerating, so those two forces must add to 0. So the observation is that because there's 0 acceleration, that implies that these two forces have to have the same magnitude. Are there any forces acting on the lower book that have the same magnitude as a force acting on the upper book? Yes, it's because there's a Newton's third law force pair. The normal force of the lower book on the upper book with the normal force of the upper book on the lower book. So Newton's third law says that those two forces are equal in magnitude and opposite in direction. Compare the free body diagram for the lower book to the free body diagram for the same book before we added the upper book. Okay, so that was before, and after we add the new book, we get an additional normal force pushing down, and that is going to increase the amount of normal force that the table has to provide. So the gravity force in the lower book stayed the same. The normal force pushing upward on the lower book had to increase once you place the upper book on top of it. And there's a third force that appeared, the normal force between those two books. Identifying Newton's third law of force pairs. A student says, I think that the normal force and the weight are a third law force pair. They're the same size and point in opposite directions, so they must be a third law pair. That student is wrong. A third law force pair has to be the same type of force. It has to be gravity and gravity, or normal and normal. And we've already discussed this answer number one. It's the Newton's third law force pair is this. So it's two normal forces. The student is correct that the normal force and the weight are equal in magnitude. They're equal in magnitude because that book is not accelerating, so those two forces add up to give you 0. What third law force pairs are shown in the diagrams you've drawn? Identify them by drawing some X's. So we can take this guy and do its Newton's third law pair over here. So they both get X's to indicate that third law thing. There's only one pair. Can both members of a third law force pair appear on the same free body diagram? No. Once again, in a particular free body diagram, you only draw forces acting on that one object of interest. In a third law force pair, there are two objects of interest. There's the lower book on the left-hand side, there's the upper book on the right-hand side. So you would only have this force on the upper book's free body diagram. You'd only have this force on the lower book's free body diagram. And last question. Can members of a third law force pair be different types of forces? Could one be a gravitational force and one a frictional force, for example? No, they can't. Newton's third law is just talking about one type of force, and when you have a normal force, for instance, between two objects, it's the normal force of object 1 on object 2, and its pair is the normal force of object 2 on object 1. Same thing for gravity, same thing for friction. Any type of force has an equal and opposite reaction force that is the same kind of force. Okay, and that's the end because we're not doing page 30.